Okay, hello and welcome everyone. So this is the solution walkthrough for the first exam from Intermediate Micro in spring 2024. Now, if you've already taken the exam or you watched that video and tried the exam, maybe all you want to do is see the solution. That's this right here. I'll do the walkthrough carefully in a little bit, but this very beginning is just me showing what the answers are. All right, so if you just click through this video and you didn't already take the exam or didn't have a chance to see that previous video, I'll link it up in the description and then as a comment so that you'll be able to do that and then come back to this one. All right, so the first question, we can summarize the idea behind constrained optimization with which of the following? Consumers simply living their best life kind of feels like just optimization, unconstrained optimization. It always depends on the circumstances. It's pretty much just the constraint. It's like climbing a mountain, you do because it's there, and if at first you don't succeed, try again. Those are just throwaway phrases from probably popular maybe 50, 75, 100 years ago. The consumer is doing the best they can given the circumstances is the best answer. Doing the best they can is like the preferences, and then given the circumstances is the constraint. So constrained optimization. If I truly believe Coke and Pepsi are interchangeable, where X is Coke, Y is Pepsi, my preferences are best represented by which of the following? It's this one. This is the only perfect substitutes amongst this collection, right? So if they're interchangeable, I presumably can trade them one for the other at some constant rate. That's perfect subs preferences. It's definitely not complements. Then you need to use them together. And it's not Cobb-Douglas. D is incorrect. It says we can't know this without a budget constraint, but we certainly can because we only need to know something about preferences from a statement about preferences. We don't need to know anything about prices or income to be able to determine what's a person's utility function. If prices are the same and two consumers are observed optimally selecting the same bundle consisting of good X and good Y with the positive amounts of both, we have an interior solution. It's not a corner solution. And so in terms of what we can learn here, well, the first couple are just phrased in terms of must, like we're required. So it says both must have preferences indicating that the goods are substitutes. I mean, they could be. You very well could have preferences that are perfect substitutes that are consistent with this, but they don't have to be. Same thing with perfect complements. So both must have preferences indicating that the goods are perfect complements. They could be, but we're not required to have perfect complements because consumer could have Cobb-Douglas preferences. D is incorrect. It says neither can have Cobb-Douglas preferences for this to be true. No, because it will be true when we have Cobb-Douglas preferences. Because after all, what's happening is if we have an interior solution, we have positive amounts of both goods. The two consumers have the same prices, which means they face the same price ratio. And at the optimal, they want the price ratio to equal the marginal rate of substitution. So the best answer is both consumers must have the same marginal rate of substitution at the optimal bundle. Right? Now, could be that they have perfect substitutes preferences, could be that they have perfect complements, but they're not required to. So the fact that it says that they must is incorrect. Find the optimal bundle for the consumer with utility function. Well, these are Cobb-Douglas preferences, X times Y, facing prices. Price of good X is 3, price of good Y is 4, income is 24. So here what I'm going to do is I'll find the marginal rate of substitution. That's the ratio of the marginal utility of X to the marginal utility of Y. The marginal utility of X is Y. The marginal utility of Y is X. What I'm doing, I'm taking the partial derivative. And I'm going to take the partial derivative of this with respect to X. And if I take the partial derivative with respect to X, I can treat Y like a constant. It might as well be like 2X. Take the derivative of 2X with respect to X, it's 2. So if I take the derivative of this with respect to X, it's Y. And then if I take the partial derivative of this thing with respect to Y, it's just X. It's as if this is like 3Y or something. So take the derivative of with respect to Y of the function 3Y, it's just the coefficient. It's just the 3 part. Well, here it's just the X part. So the partial derivative of the utility function with respect to X is Y, with respect to Y is X. Marginal utility of X divided by marginal utility of Y is my marginal rate of substitution, which equals the price ratio, the slope of the budget constraint, Px over Py at the optimal. So that's given by this expression, 3x is equal to 4y. Okay, good. So I can drop this into my budget constraint now, and turns out, since the price of good x was 3 and price of good y was 4, I can substitute 3x directly with 4y. I get 8y is 24, and then that's going to come out to be 24 divided by 8. Y is 3. If y is 3, then x is 4. So the correct answer is 4, 3, D. All right, so this was a different version of the exam. And so I'll skip over this in just a second. I'll come back to that. The next question we need is right here. So question 5 was, suppose the consumer has utility given by x plus y, where good X is money and good Y is pizza. The price of pizza is $5 per slice. The consumer has $25 available to allocate. Which is true? Well, we can find our marginal utility of X. That's the coefficient on X. Marginal utility of Y is the coefficient on Y. These are perfect substitutes preferences. Equivalently, we take the partial derivative of this with respect to X, it's 1. Partial derivative with respect to Y, that's 1. So there's my marginal utilities. So my MRS is 1. What's my price ratio? Well, it's 1/5. Because the price of pizza is $5 per slice. What's the price of money? It's $1 per dollar. And so the price ratio is going to be 1/5. Turns out my MRS is going to be steeper than my slope of my budget constraint is going to be flatter than my indifference curves. My indifference curves are steeper than my budget constraint. And so that's an ALEX solution, all X solution. Well, that entails we're never going to buy pizza because good X was money. So we're keeping all our money, right? And so the best answer is C here. So I think I lost my annotation tool, so let me get that. But I had this correct on the answer sheet if you would have seen that. The answer here is A. So the next one was the absolute value of OR's marginal rate of substitution as current consumption bundle is greater than 3. That is marginal utility of 1 divided by marginal utility of 2. The MRS is greater than 3. OR's has convex preferences and is currently consuming positive amounts of both goods. And the best answer here is A. I'll show this with a picture, a couple of pictures. You might have thought more than one would be true. That's not correct. And you might have thought that none of them are true so let me go over this carefully. So here is the problem. This is actually question 6 on the exam. These are option 1 was option A, option 2 was option B, option 3 was C, 4 was D, and then 5 and 6, who cares about? So I'm going to talk about each of these. So the best answer is answer 1. So being that marginal rate of substitution is greater than 3 means we're on the vertical portion of convex indifference curves, right? So we know ORS has convex preferences. We're thinking of like Cobb-Douglas preferences. They're very steep along the y-axis. They're very flat around the x-axis. Since MRS is greater than 1, matter of fact, it's greater than 3, we know we're on the steeper portion of the axis. Of the indifference curve as we're going towards the y-axis. So what's going to happen? I say to establish 1, it's just enough to show that moving back 1 and up 3 will place ORS on a lower indifference curve, right? Because this is saying taking away sum of good 1, giving ORS sum of good 2, or giving ORS 3 units of good 2 makes ORS worse off. So let's see that. We start right here at a bundle 2, 9. Suppose we take 1 away. We move to 1 unit of X and we give ORS 3. So we move up from 9 to 12. Oh, we're on the lower indifference curve, right? And so what's happening is with convex preferences, the MRS, let's just say it was 3. It's greater than 3, but suppose it was 3, we'd be looking at this tangent line, which, it's going to, if we walk back from here, 1 and up 3 along a line of slope of -3, we're going to clearly be on a lower indifference curve. Even if MRS was 3 at the current bundle, kind of as I drew, this is true. All right, so, and that was the comment right here. So I just wrote that out as I said, because starting at the point of 2, 9, taking away 1x, replacing with 3, y necessarily places ORS on a lower indifference curve. When reaching the new bundle, 112. That's consistent with 1. Numerically, suppose ORS has utility of 18 at that bundle. MRS is going to be 4.5, which is greater than 3. Suppose ORS moves up to 112, which has marginal rate of substitution of 12, which is greater than 3, but utility of only 12. So we show that ORS started at a place with a higher marginal rate of substitution than 3, took away 1x, got 3y, and was moved to a lower utility. Okay, so now I'm going to look at, this establishes 2 going in the other direction. So ORS is not necessarily better off. What was 2 saying? 2 is saying taking away sum of good 1 and gives ORS sum of good 2 will not necessarily make him better off. Yeah, it didn't necessarily make him better off because all we need is to show one example where, it's not necessary. Okay, so what was the phrasing? So 2 is like 1, but it says taking away 1 of good x and giving 3 of good y, right? Moving up and to the left on a line, on a tangent with a slope of 3 will necessarily make him better off. To disprove this, we just need a counterexample, right? And so I have a counterexample. We just did that. So we showed that ORS is worse off. Okay, so question 3 No, item 3, item C, was saying giving Ur sum of good 1 and taking away 3 units of good 2 will necessarily make him worse off. And then number 4 was giving sum of 1 and taking away 3 will necessarily make him better off. And again, I'll show those both together. So 3 requires that giving him 1x and taking away 3y has to make him worse off. Well, what if we started a point that's like really steep? So I say to show number 3, we actually just require the reverse of a, number 1. We can draw it more extreme. Suppose the dotted tangent line has a slope of 6, which is certainly consistent with MRS greater than 3, if that's the tendency there. Urs is currently at the bundle 1, 6, okay, because that'll give us an MRS of 6. We can give Urs 1 more x and remove 3y, so Urs reaches the point 2, 3, which is on the same indifference curve, because these are Cobb-Douglas preferences. So my utility level is going to be x times y. So 6 times 1 is 6. 2 times 3 is 6. Okay, they're on the same indifference curve, same level of utility, which tells us Urs is not necessarily worse off. That establishes 3. And is also not necessarily better off, because Urs is the same utility, right, which establishes 4. We can see this numerically just kind of written out. Just what I said. Right? But that's all we need to be able to establish that the correct answer for that one is A. Okay, so next thing we want to do is question 7. So for 7, this was remember I said this is from a different version of the exam. To show you this one, I have to skip down here and I have to do this one. Okay, what was different? I changed the prices. I didn't like that this involved the square root of 2. It actually works out nicely if you leave it as square root of 2, but if you don't, it's horrible. And so I swapped out this price for 1. What was the problem? What was the question? Consider a consumer with the utility function of Cobb-Douglas preferences, x times y, faces prices of 1 and 1. Set up the Lagrangian and find the cheapest bundle possible to attain utility of 25. So this is the consumer's utility maximization problem. We want to find what the income has to be able to purchase that bundle as well. So we do this right here. Utility is these Cobb-Douglas preferences. Prices are 1 and 1. Find the cheapest bundle to attain such that utility level is going to be 25. Okay, so the Lagrangian function is going to bring my objective function, the expenditure, and the constraint into one single function. So in one fell swoop, I can deal with both. So this involves introducing the Lagrangian multiplier, which is basically, we can interpret it for now as the penalty for violating the constraint. Because if you satisfy the constraint, this is 0, so to be lambda times 0, you don't incur lambda at all. However, if we violate the constraint, for each 1 unit violation of the constraint, you'll incur lambda, right? Which will deduct, in this case, from the expenditure, if it's, well, either way. So let's not go off into the weeds on that one. So I did it initially with the generic version. I used a generic budget constraint. We don't need to do that. We have the prices. They're 1 and 1. So this is my expenditure. I said generic constraint. One of the mistakes, one of the pitfalls is treating this like a budget constraint. It's not. This is the expenditure on X. This is the expenditure on Y. We're trying to come up with the cheapest bundle. We're trying to minimize expenditure. That's the objective function. The constraint is we're trying to hit this utility with Cobb-Douglas preferences. So anyway, I initially used the generic expenditure, and then I also did it analogously with, or side by side in parallel, where I plugged in this prices. So either way, what I'm going to do is I'm going to take the partial derivative of this thing with respect to x. So if I use the generic version, it's going to be p1 minus lambda x2, right? Because this is like a constant. This is like a constant with respect to x1. So is lambda. If I take that partial, and if I take the partial with respect to x2, it's going to be p2 minus lambda x1. Or if I use this one where I already made the substitution of prices, same thing, I'm just going to get 1 minus lambda x2 or 1 minus lambda x1, which I can make the substitution for prices right here. This, if I put in prices of 1 and 1 for these, I get that immediately. So however you want to do it. All right, so ultimately we want to find our tangency condition. So I need to solve for lambda, and then I'm going to set the two equal to each other. So this right here is going to be solving for lambda, p1 over x2, and then p2 over x1. Or I could put in ones here, so this would be 1 over x2 and 1 over x1. However, whichever order you want to, wherever you want to make that, make use of this information about the actual prices is fine. I waited kind of late, and I did this down here. It turns out anyway at our tangency, x2 is equal to x1, which is really helpful because my utility function was x1 times x2 is equal to 25. So now I've got x1 squared is 25. So I've got x1 is 5. So x2 is 5. So that's my expenditure minimizing bundle. This is the cheapest way possible to attain utility of 25 with these preferences as 5 and 5. What's the income required to buy this? Well, at a price of 1 for each of these, it's going to be $10, or like 10 is my income, whatever is the monetary units. All right, so that was for question 7. Now I've got to do question 8, which was actually on here still. So consider a consumer with utility function complements. This meant to be a comma there. And facing prices of 1 and 1, solve for the cheapest bundle possible to attain utility of 100. Remember, for solving the expenditure minimization problem with complements preferences, what I need to do is I need to set whatever's on the left side of the comma equal to the utility level, and whatever's on the right side of the comma equal to the utility level, which in this case tells me that my utility has to be, my amount of each has to be 100. So I need 100 units of x1, 100 units of x2, because if I plug that in, what's the smaller of 100 and 100? 100, right? And that's going to be my utility level. And what's the cheapest way? Because I have to hit this. I mean, that bundle is going to be the cheapest by default because that's what I need to do to be able to hit 100. There's other bundles I could do that would also hit a utility of 100. Like I could have 100 units of x1 and 1,000,000 units of x2, but that's not the cheapest way to get utility of 100 because it's super wasteful. If I had 1,000,000 units of x2 and only 100 units of x1, then my utility is going to be the smaller of these that would still return utility of 100. But then over here, I'd have 100 x1 plus 2 times 1,000,000, 2,000,000 x. That'd be ridiculous, right? So the cheapest way to attain utility of 100 with these preferences is to have 100 of each of good 1 and good 2, which is going to cost me 100 for my expenditure on good 1, 2 times 100 or 200 for my expenditure on good 2, that'll be 200. What's the income that I need to be able to purchase this bundle? Oh, it's just that 300 that I found right there. Actually, I think I probably should have put that work down there from the get-go. All right, so that was question 7 and question 8. Now question 9, consider a consumer with utility function square root of x plus y. This is quasi-linear preferences. So what I'm going to do is I'm going to find the marginal utility of x. So I'll take the partial derivative of this with respect to x. It'll be 1/2 times x, reduce the power by 1. So it'll be 1/2 x to the minus 1/2. Then I'll take the partial derivative of this thing with respect to y. That'll just be 1, and that's my marginal utility of y. Written this way, we see my MRS is just 1/2 x to the minus 1/2, because I'll draw like a division bar right here. And my MRS is this thing, but it doesn't matter because that's divided by 1. So my MRS right here equals my price ratio, 1/4, will help me find my solution. Solving here, what can I do? Well, I can if I want, I can cancel or cross multiply or whatever. Suppose I multiply both sides through by 4. I'll get a 4 times square root of x is equal to 2, and then I'll divide through. I'll have to move this to the other side, and ultimately I'm going to have 2 is equal to the square root of x. I'll square both sides, and then I'll get x is 4. If x is 4, but I have to exhaust my budget, so I'll write my budget constraint. This is going to be 1 times the amount of x plus 4 times the amount of y is equal to 12. My expenditure on x is going to be 4, which is going to leave 8 units to spend on y. So, 8 monetary units to spend on y at a price of 4 tells me I'm going to buy 2 units of y. So my optimal bundle is going to be 4 and 2. Now find the optimal bundle if the consumer has income 4 and faces prices 1 and 4. So what's changed? Well, the price ratio is the same. My preferences have changed, are the same, haven't changed, but my income changed. So I'm going to skip right down here to working on the budget constraint. So now it's going to be 1 times 4 plus 4 times y is equal to 4. Oh, this tells me I'm not buying any y. I'm still going to buy the 4 units of x. Find the optimal bundle if I have income 4 and faces prices of 2 and 4 for x and y respectively. Well, now my price ratio does change. And so I have the same MRS, but it's going to be equal to a price ratio of 1/2 now. This is going to tell me I'm going to want 1 unit of x. If I have 1 unit of x, how much y am I going to demand? Well, my income of 4 tells me I'm going to have, 2 units available to buy my y. So I can buy half a unit of y. Okay, so question 10, consider a consumer with utility function, Cobb-Douglas preferences, so it's going to be x to the 3/4, y to the 1/4. Use the Lagrangian and find the consumer's optimal consumption bundle, assuming a generic budget constraint. You can apply a monotone transformation if you know it. So that would amount to taking the natural log of this thing, and then the utility function you'd be working with would be 3/4 natural log of x plus 1/4 natural log of y. You take the partial derivatives, which would work out really nicely, and then you get your margin rate of substitution, just like that. I didn't do it that way. I took the partials, I wrote out the Lagrangian with the original objective function and with the budget constraint, and then I took the partials in turn and then solved kind of the long way. So if I take the partial derivative of this with respect to x, it's going to be 3/4 x to the minus 1/4 because you'll reduce the power by 1. Don't lose this y to the 1/4. That's a constant. It comes along for the ride. It sticks right there. And then don't forget about my minus lambda px. Over here, it's going to be 1/4 x to the 3/4 y to the minus 3/4 minus lambda py. And so for the same reason, so multiply this thing by this coefficient, reduce the power by 1 is why I have y to the minus 3/4. Solving for lambda gives me basically my bang for your buck condition. This is marginal utility of x divided by price of good x. This is marginal utility of y divided by price of good y. I can cross multiply to get this as MRS is equal to price ratio, and then just canceling. So 3/4 divided by 1/4 boils down to just 3/1. X to the minus 1/4 minus 3/4 is x to the minus 1, which places x in the denominator. Y to the 1/4 minus 3/4 is is y to the 1, which places y in the numerator. And then this is equal to my price ratio. Cross multiplying, I find px x equals 3y py. So when I substitute, I'm going to substitute for this entire thing. I'm going to replace in my budget constraint px x with 3py py right here. So I get 4py, y is equal to m. And then I find my demand, Marshallian demand for y is going to be m over 4py. Correspondingly, I could use this equation right here to find my demand for x, or I could go back to my budget constraint like I did. Solving, I find my demand for x is 3/4 m over px. Also, we can check this with our known Cobb-Douglas demands. And so Cobb-Douglas demands for x are going to be alpha, where this is alpha, over alpha plus beta, where this is beta, times m over px. So it's going to be alpha, 3/4 m over px for x. It's going to be beta, 1/4 times m over py for y. All right, true or false, this consumer will always spend 3/4 of their income on good X, show or explain. It's true. So we found that just from our demand here. We just need to show the expenditure is equal to 3/4 of my income. True or false, consumer always spend 1/4 of their income on good Y. True. My expenditure on Y is always 1/4 of income. True or false, regardless of what happens with X, if M is 24 and Y is 3, or price of good Y is 3, consumer will buy 2 units of Y. Show or explain? Well, we can use this right here. I'm going to spend 1/4 of my income on Y. So 1/4 of my income of 24 is 6, which with the price of Y being 3 says I should buy 2 units of Y. Yeah, that's what I did. I didn't mean to draw a line there, but it actually worked out kind of nice. True or false, regardless of what happens with X, M is 24, Y, price of good Y is 6. Consumer buys 3 units of X. That's true as well. Same sort of process. I'm going to spend 3/4 of my income on X. 3/4 of 24 is 18. Divide by the price of 6 tells me I want 3X. True or false, it doesn't matter how much the consumer is currently consuming. They'll always trade Y for X at the same rate. False. The MRS depends on the bundle, right? This would be true if we had perfect substitutes preferences. And then the previous things would all be false. But here we have Cobb-Douglas preferences, which clearly depends on the composition of the current composition of the bundle. All right, so suppose Max insists on consuming 2 spoonfuls of Cocoa Puffs with exactly 5 spoonfuls of Honey Nut Cheerios. Write down Max's utility function. So this is going to be perfect complements because we know we have exactly some ratio of Cocoa Puffs to Honey Nut Cheerios. What's this going to be? Well, what you can do is you can find the first bundle that they're definitely going to accept, which is let X be 2 and Y is 5. Or we could double that. So X is 4, Y is 10, or we could triple that. So then it would be 3 and 6 and 15. So what's the ratio? The ratio is Y is always equal to 5/2 X. So if Y is equal to 5/2 X, I can multiply through by 2. So 2Y is equal to 5X. I can replace that equal sign with a comma and drop this into my utility function. Now that I've got this, right, if I replace the comma with an equal sign, I get the line through the origin that collects all the right angles, right? So the ray through the origin is going to be given by, that's this thing, is going to be given by this equation right here, is what we found. Okay, so we have our utility function. We can check this with the bundle that we had. So let's evaluate 5 times 2, 2x, that's 10. 2 times 5, that's also 10. So this will return the same value on both sides when we try the test bundle that Max definitely prefers. Okay, so this is the correct utility function. Incorrect utility function would be 2x comma 5y. This is the correct one. And then if you tried that one and tested that bundle, it wouldn't work. You'd find that you're on one of the wings of the indifference curves if you had the wrong utility function. Anyway, so suppose we have income of M, and we have price of good X is 10, price of good Y is 4. Find the optimal consumption bundle. Well, I can drop this relationship into my budget constraint. So 10x plus 4y, let's replace y with 5/2 x. Solving, I find x is equal to m over 20, just like the one in class. And then y is going to be 5m over 40, or m over 8. We can also get that from using this right here. And, that's actually what I did. So you could go back to the budget constraint and solve for y, or you could use that. I think I did this. Oh yeah, I did this over here. I solved using the budget constraint. That's why I was, whatever. So what's Max's utility at the optimal bundle? Max's utility at the optimal bundle is going to be m over 4, right? So 5 times m over 20 is 5m over 20. 2m over 8 is going to be, 2m over 8. 2 times m over 8 is going to be 2m over 8. That boils down to m over 4 and m over 4. Right? All right, so let's see. Consider 2 consumers with the following preferences. Consumer A is always willing to trade 2 units of X for 1 unit of Y. That tells me I'm going to have an MRS of 2, right? So I'm going to go down 1 over 2. That's an MRS of 2. Always willing to trade 1 unit of X for 2 units of Y. That's down 2 over 1. Whoops, I didn't mean to do that. So that's an MRS of 2. So let's see, MRS of 1/2 is going to be given by, I can just make these my marginal utilities. So one utility function that would represent A's preferences is X plus 2Y. Look at the MRS of this. It's that 1/2, which captures that statement. One utility function that will represent B's preferences is 2X plus Y. Yep. There's other utility functions. You could take a monotone transformation of this, and that would work as well. But this is the simplest one. I'd expect most people did that. If both consumers have income 12 and face prices of 1 and 1 for each, which is Allie and which is Alex? Well, it turns out Allie is consumer A and Alex is consumer B. So if the MRS is greater than the price ratio, where Alex will consume all X, that was consumer B, MRS greater than a price ratio of 1. And Allie is MRS less than the price ratio. So MRS is 1/2, price ratio is 1, so that was Allie. Okay. And then lastly, suppose a consumer, or examine a consumer's budget with the following conditions. Consumer has $30 available to spend on 2 goods, X and Y. While price of good Y is 2 no matter what. The price of good X is governed by this scheme. Consumer has a coupon that reduces the price of the first 6 units down to $1, but pays the full price of 3 for all subsequent units. All right, so the way that I want to build the budget constraint is first pin down the vertical coefficient, intercept, because I know that the price of good Y is always going to be 3. I have $30 available. This is going to be 15, always and everywhere. Then what I want to do is I want to find out how much have I spent by the time I get to the kink. So the kink is going to occur after 6 units. How much is it going to cost to get 6 units of X? Well, the first 6 units is 3. First 6, I was looking at this. First 6 units is 1. So that's going to cost me $6. That's going to cost me 6 of my $30 to get here. I have $24 left over. Spending $24 on good Y, which has a price of 2, allows me to buy 12 units of good Y. So that gives me my coefficient, or my coordinates for the kink, 6 and 12. And then if I were to continue to spend on good X after I bought the first 6 for $1 each, now I'm buying the remaining however many for $3 each. I have $24 divided by 3 tells me I can buy 8, which brings me from 6 to 14. Right. The slope of the budget constraint is going to be 1/2 up here, and it's going to be 3/2 down here, just from the price ratio. If the consumer's utility is given by 2x plus by, what value of b guarantees the consumer is alley and only consumes y? So I just need a budget constraint. Sorry, I just need a value for beta such that the MRS is always flatter than the budget constraint. So I just need this to be flatter than 1/2. So I need b to be greater than 4. Because if b is equal to 4, then my MRS would be 1/2, right? So it'd be 2 divided by 4 would be 1/2, but then that would lie coincident with the flat part of the budget constraint. If I had a larger denominator for my MRS is going to be, right, MRS is going to be 2 over beta. It's my MRS. That kind of worked. I need b to be bigger than 4 so that my MRS is smaller than 1/2 because I want something flat. I don't even have to worry about this bottom part because this has a price ratio that's much steeper. All right, so beta greater than 4 is the answer. Find the optimal bundle for a consumer with preferences represented by a minimum of 2x and y, right? Well, the line through the origin that collects all the possible candidate solutions is going to be y equals 2x because I'm going to replace this comma with an equal sign. It'll be the line y equals 2x. That's this right here. I can go to the budget constraint to find my solution, but actually if I'm a little bit clever, I don't need to do that at all because this is just that point 6/12, right? The ratio, the relationship at the optimal between y and x is y is double x. When is y double x? Oh, like right there, 6/12. So there's my solution. Matter of fact, well, that's, hey, it kind of fixed it for me a little bit. That's almost the line. If this goes through the origin, that's the line. Maybe I'll make this look like this. There we go. This is the line that's going to connect all my, corners of my indifference curves. Anyway, so let me show you just the answer sheet one last time that had all these things on it. And then I'll go ahead and conclude. I hope you enjoyed the video. I hope you enjoyed the test. I hope you did well. And I will see you next time.